Hi folks, now that we've learned how to calculate molar mass, we're going to learn how to use molar mass to do some more dimensional analysis doing molar conversions. We have learned two sets of conversion factors that have to do with moles. We've learned how to switch between moles and particles. There are two conversion factors that let us do it depending on which direction we're going. We either go from particles to moles using this conversion factor, or from moles to particles using this second conversion factor. The other conversion factor that we've learned, although we haven't used it yet, is going from moles to mass. So we can go from mass to moles using this first conversion factor, or we can go from moles to mass using this second conversion factor. When we learned this first conversion factor, it didn't matter what substance we were using, because it doesn't matter, just like dozens. It doesn't matter if you have a dozen donuts, a dozen bagels, a dozen eggs, a dozen cookies, a dozen elephants. 1 dozen is 12 items. It's the same thing with moles. 1 mole is 6.022 times 10 to the 23rd. When you convert from moles to mass, it does matter what particle you're talking about, because each particle has a different mass. So think about it in terms of dozen again. A dozen elephants weighs more than a dozen donuts. So every time you do a moles to mass conversion, you're going to need to calculate that molar mass, like we learned in the previous video. When do you use which conversion factor? I'm giving you this kind of conversion factor flow chart here to help you out, because we will learn more conversion factors this semester. So getting used to this idea now will be helpful to you, I hope. So what conversions involve moles? Right now, the moles are the center of our chemistry universe. We're learning how to convert from mass to moles, and we're learning how to convert from particles to moles. Notice that you cannot go from mass directly to number of particles. You cannot do that. You have to go through moles and then convert to number of particles. Similarly, you cannot go from number of particles straight to mass. You must go through moles. Moles are the center of this chemistry universe here. So, how do we do it? What are our conversion factors? We learned that to go from moles to number of particles, we need to get rid of moles and bring in particles. To go from particles to moles, we need to get rid of particles and bring in moles. So this is like the conversion factor. This arrow is like the line in the fraction of the conversion factor. Those are the ones we learned a couple lessons ago. The new ones we're learning today, or applying today, are converting from mass to moles. We get rid of the mass by dividing by molar mass, and we bring in moles. Or if we want to convert from moles to mass, we get rid of moles and bring in the molar mass. So let's do some conversion practice using using dimensional analysis and using these conversion factors. How many moles of carbon are in 26 grams of carbon? This is my known. I'm given the most information about carbon, grams of carbon, the mass of carbon, and I'm trying to calculate how many moles of carbon I have. Well, writing this out, my known is 26 grams of carbon. I'm trying to calculate for moles of carbon. I have to insert the correct conversion factor. I want to get rid of grams and bring in moles. That means I'm going to have to get rid of grams with the molar mass of carbon and bring in moles up top. 1 mole has a mass of 12.01 grams. So this is the correct conversion factor to use to get rid of those grams. Doing the multiplication and the division, I'm doing 26 times 1 divided by 12.01. Doing the math, you get 2.2 moles of carbon. 2 significant figures because my limiting number of sig figs comes from this value here, 2 significant figures. Let's do another example. Find the mass of 2.30 moles of water. My known is 2.30 and my unknown is the mass, so that's what I'm trying to solve for, grams of water at the end. I want to get rid of moles and convert to mass. This time, my mass ended up on top because I'm trying to get rid of these moles and convert to grams. So grams is on top, and the molar mass of water is 18.02 grams per mole. We've done that calculation already, but it's because water is H2O. Each hydrogen has a mass of 1.01, and there are 2 of them. And then we have the mass of oxygen. And this adds up to 18.02. If we do the math, 2.30 times 18.02 divided by 1 gives us an answer of 41.4. And of course, we're sticking to 3 significant figures because that is the limiting number of significant figures in the problem. Another example. How many moles of sodium chloride do you have if you have a 10-gram sample? So my known is that I have a 10-gram sample of sodium chloride. That's NaCl. Sodium has a charge of +1 and chloride has a charge of -1. My unknown that I'm trying to solve for is the number of moles. So I'm starting with a 10-gram sample of NaCl, and I'm trying to solve for the number of moles of NaCl. I want to get rid of grams and bring in moles so that that cancels out. But I need to calculate what the molar mass of sodium chloride is. So I look up sodium on the periodic table. There's just one of them, so 22.99. And I look up chlorine on the periodic table. There's just one of them, and that's 35.45. So when I add those together, I get 58.44 grams per mole. 58.44 grams per 1 mole. Doing the math, you multiply by everything that's up top, you divide by everything that's down below. 10 times 1 divided by 58.44 gives you the answer 0.1711. Notice that I can use 4 significant figures this time because I have 4 sig figs in my known as well as 4 sig figs for my molar mass. Find the mass of 2.10 times 10 to the 24 molecules of sodium carbonate. Alrighty, my known is the molecules. I know the number of molecules, but I want to find the mass. That's my unknown. I don't know any conversion factors to go from molecules to mass. I can't do that in one step. I know how to go from molecules to moles. I know how to go from mass to moles, but I can't do both in one step. If you don't see moles as one of your, either your known or your unknown, you know that this is going to take multiple steps. I'm going to have to convert from mass to moles and then from moles to molecules. So let's look at how we do that. We write the known first, and I'm leaving space for 2 conversion factors because I'm going to have to go from molecules to moles and then from moles to mass. My final answer will be a mass, so I'm writing down grams of sodium carbonate. How do I convert from molecules to moles? That's when I use Avogadro's number, because a mole is always 6.022 times 10 to the 23rd. So I'm going to divide away molecules. There are 6.022 times 10 to the 23rd molecules in 1 mole of sodium carbonate. And those molecules are going to cancel out. Now I'm going to have moles as my unit, but I don't want to have moles as my final unit. I want grams as my final unit. I want to get rid of moles and bring in grams. So my second conversion factor is going to be from getting rid of moles and converting to grams. Now, in order to convert to grams, I need to know the molar mass of sodium carbonate. But the molar mass of sodium carbonate is just going to be calculated from doing 2 atoms of sodium, and each of those is 22.99 grams per mole. And then I'm going to add in my 1 carbon, which has a molar mass of 12.01. And then I'm going to add in my 3 oxygens, each of which has a mass of 16 grams per mole. So when I add those all together, that's where the number 105.99 comes from. This is starting to get more complicated in terms of the math. I now have a number times 2 fractions here. I recommend multiplying all the numbers that are up top, multiplying all the numbers that are down below, and then doing one large division problem. So, doing this top multiplication problem, I'm going to do 2.10 times 105.99, which is going to give me 222.579. Times 10 to the 24 is my only piece of scientific notation in the numerator. And then in the denominator, I'm just doing 6.022 times 10 to the 23rd times 1, which gives me 6.022 times 10 to the 23rd. And when I do that division then, divide the coefficients and subtract the exponents, that's going to give me, when I just divide the coefficients, that's going to give me 36.96, I'll go ahead and round that up, 961 times 10 to the, now I'm going to subtract the exponents here because it's a division problem. 24 minus 23 is 10 to the first. So 36.961 times 10 to the first. That's not correct scientific notation. And scientific notation isn't really necessary here because it's just times 10 to the first, which is the same as times 10. So really, I'm going to have 369.61. We also need to think about significant figures. My limiting significant figure value here is my initial given known value with 3 significant figures. So our final answer is going to be, to 3 significant figures, 370. Just to be clear on that, because the rounding is a little silly, 369.61. We're going to round off after 3 sig figs, but we have to bump this up because the number after our cutoff point is 5 or higher. So we have to round up to 370, but we want our number to have 3 sig figs. I want this 0 to be significant, so we need that decimal point to make that 0 significant. Example 5. How many atoms of aluminum are in 15 grams of aluminum foil? My unknown is atoms. My known is the grams of aluminum foil. Think about how many steps you think this process is. This is a 2-step process. because I don't see the word moles here anywhere. So I'm going to have to go grams to moles, then moles to atoms. My known value is 15.0 grams of aluminum, and my final value is going to be atoms of aluminum. And as I'm thinking about this, I'm thinking atoms are tiny. I bet my answer is going to be huge. I'm expecting a really huge number for my number of atoms. So let's look at this. This is, as I said, going to be a two-step process. I'm going to have to convert from grams of aluminum to moles of aluminum. And I need to think about how many grams are in 1 mole of aluminum. That I can just look off of the periodic table. There's just 1 atom of aluminum. So straight off the periodic table, 26.98 grams if I round to 2 decimal places. And then I need to convert from, let's see, hold on, those grams cancel out. So now I'm going to be left with moles. I want to get rid of moles because that's not the final answer I want. Get rid of the moles and convert to atoms of aluminum. I know that 1 mole is the same as 6.022 times 10 to the 23rd atoms. So doing my multiplication, up top, I'm going to have, let's see, 15.0 times 6.022 is 90.33. But don't forget your scientific notation there, times 10 to the 23. Down below, I'm just dividing by 26.98. So when I do my division, I'm going to divide those coefficients. And there's no subtraction for me to do here. So I'm going to get an answer of 3.34804 times 10 to the 23rd. That doesn't have the right number of sig figs. It is correct scientific notation though. My coefficient is a number between 1 and 10. But my answer should only have 3 significant figures because of this, my given, my known value. So let's round after 1, 2, 3 significant figures. I'm going to bump that number up, and I get 3.35 times 10 to the 23rd atoms of aluminum. Let's do one last example. Determine the mass, that's our unknown that we're trying to figure out, of 4.65 times 10 to the 22 atoms of xenon. This is my known value. So I'm starting with my known value of 4.65 times 10 to the 22 atoms of xenon, and I'm trying to work my way to finding out the grams of xenon at the end. I'm not converting to or from moles here, but I have to go through moles. This is going to be a two-step process. So I'll leave room in my dimensional analysis for 2 conversion factors. I have to get rid of my atoms. I have to get rid of my particles by converting to moles. And I know that I have 6.022 times 10 to the 23rd atoms of xenon in 1 mole of xenon. But I don't want moles as my final answer either. I want to convert that to grams. So I want to get rid of moles of xenon and convert to grams of xenon. And by using the periodic table, I see that 1 mole of xenon has a mass of 131.29 grams. I check my conversion factors to make sure that they make sense and that my units cancel out. Atoms cancel out with atoms. 1 mole is a bunch of atoms, that's right. 1 mole has a mass of 131.29 grams, that's right. My moles cancel out and I'm left with grams as my final answer. Good, so now I can do the math. When I do the math, I'm going to multiply everything up top and get a value for my numerator and multiply everything down below and get a number for my denominator, and then I'll do the final division. So 4.65 times 131.29 gives me 610.29 0.4985, but I can't lose my scientific notation there. I have to remember to include it. And down below, 6.022 times 10 to the 23rd times 1 is just 6.022 times 10 to the 23rd. I'm going to determine my final answer by dividing the coefficients and then subtracting the exponents. So 610.4985 divided by 6.022 gives me 101.378. Yeah, that makes sense. 600-ish divided by 6 is about 100. And when I subtract my exponents, 22 minus 23 is -1. Now, this is not correct scientific notation because my coefficient is not a number between 1 and 10. But also, scientific notation doesn't really look necessary in this example because my exponent isn't very large. So I'm just going to go ahead and multiply times 10 to the -1 to make this a number in standard notation. So if this is times 10 to the -1, that means make it smaller by 1 decimal place. So my final answer is going to be 10, or not my final answer. My correctly written number is 10.1378. Of course, I can't have a correct final answer until I think about my sig figs. Let's look at my original problem. 3 sig figs, 4 sig figs, 3 sig figs. So I'm going to be limited by 3 sig figs. I round my answer after 3 significant digits, and I don't have to round up, so my final answer is 10.1 grams of xenon. As always when doing math problems, check your answers to make sure it makes sense. If I'm asking you to calculate number of atoms, your answer is probably going to be very large because atoms are so tiny. But if I'm asking for a mass, that's generally not going to be a gigantic number. So one way to check to make sure that you've set up your conversion factors correctly is making sure that your scientific notation kind of cancels itself out if you're converting from atoms to grams. When you're dealing with atoms, you usually have gigantic numbers. When you're dealing with grams, generally speaking, your numbers are not that large. I hope this helped.